that intersect inside a triangle. Today we're going to talk about a couple of points a little different than what we talked about on Friday. So we're in section 5.4, and we're going to talk about medians and altitudes. So the first thing we need to know is what a median is. And before I do that, let me back up just a touch. We'll write down what a median is first, in just a second. First, what I want to say is today, the points that we're talking about today all have to, or the segments that we're talking about today, connect a vertex to the opposite side. So that's one way that these points that we're talking about today are different than the points we talked about on Friday. These points all connect a vertex of a triangle to the opposite side. On Friday we weren't worried about where the segments went. We just had to do the angle bisector or the perpendicular bisector. It didn't matter where it went through the opposite side of the triangle. All we were interested in is, did we have an angle bisector? Did we have a perpendicular bisector? Well, today our segments connect a vertex to the opposite side. So the first one is a median. The median goes from a vertex to the midpoint of the opposite side. So let's draw a median, draw a triangle and draw one of its medians. So all we need to do for a median is find the middle of a side and go to the opposite vertex. Doesn't have to be perpendicular. All it needs to do is go from the middle of one side to the opposite vertex. So this segment would be the median. Well, something special happens with the medians. We've been talking about points of concurrency. So our theorem about medians is that the medians of a triangle are concurrent at a point and what do we say concurrent means? They meet, all three meet at the same point, so they all cross at the exact same point. The three medians are concurrent at a point called the centroid. So if we draw the three medians of a triangle, they're all going to intersect at one point. We call that point the centroid. The other difference for what we're doing today and what we're doing, what we did Friday, is today we're not worried about drawing circles. On Friday, the points we could use to draw circles, we either went around or inside a triangle. Today, the points tell us some different things. So the thing that's special about the centroid is 2/3 the distance from the vertex to the midpoint of the opposite side, to the middle of the opposite side. So let's draw a picture and see what the centroid looks like and talk about what we mean by this 2/3 the distance thing that we're saying. So here is our triangle. And I'm not going to make the centroid exact, I'm just kind of guesstimate here. So we go from the middle of one side to the vertex on the opposite side. So those are going to be congruent. Those are congruent. So we'll draw another segment here. And I'll do this same one. So this would be my centroid. And let's label this triangle. I'm going to call this A, B, C, D, E, F, and G. So we're going from the middle of one side to the opposite vertex. G is the centroid. And what we mean by 2/3 the distance, if we start at a vertex, from the vertex to the centroid, so AG is 2/3 the distance all the way across. Start at a vertex here, CG is 2/3 the distance all the way across. And same thing here, start at a vertex, EG is 2/3 the distance all the way across. So we start at vertex, go to the centroid, we've gone 2/3 of the way across to the middle of the opposite side. So if we say this distance, for example, is 2/3 the distance across, what does that leave for this little piece? 1/3. So this is 2/3 of the distance, that's 1/3. So we start at the vertex, go to the centroid with 2/3 of the distance. The centroid is always inside the triangle. So our centroid is always inside the triangle. The other special thing about the centroid is that if we took this triangle, if we drew a triangle out, found the centroid, cut that triangle out of a piece of cardboard, we put our tip of our pencil on the centroid, the triangle would perfectly balance at the centroid. So we also call the centroid the center of gravity or center of mass. And that's the triangle's balance point, is at its central. So the medians can be, it can be kind of easy to confuse the medians with the perpendicular bisector. The perpendicular bisector of a side doesn't have to go to the opposite vertex, and it's always perpendicular. The median goes from the middle to the vertex of the opposite side. All right, questions about what the centroid is? It's where the medians intersect. All right, let's look at an example using a centroid. So here's my picture. And I'm going to draw some segments here. And I'll call this S, L, R, M, T, N, and P. And we know that SP, segment SP, the length is 16. And we want to know the length of segment SM. So let me highlight that. Here's SP. And we're looking for the length of SM. So this segment is 16. We want to know the length of this whole segment. So first off, what kind of segment is segment SM? Goes from the middle of this side to the vertex of the opposite side. So SM is a median. How about LT? Middle of this side to the vertex of the opposite side. Same thing, median. So point P is where the medians are intersecting. So what is point P? P is the centroid. Because P is the centroid, we know that if we start at a vertex and go to the centroid, we're 2/3 of the way across the triangle. So I'm looking at this one, I could say SP is 2/3 all the way across SM. Well, now we're set because we know SP equals 16. So 16 is 2/3 of the way across from S to M. And now we need to find SM. So what are we going to do now to find the length of segment SM? That's going to be my first step. So what is 3 doing to this side of the equation? Adding, subtracting, multiplying, dividing. Dividing, so how do we undo division? Multiply. So we want to multiply by 3. So I'm going to multiply both sides by 3. These will cancel. 3 times 16 is 48, equals 2 times SM. Now what do? Divide by 2. SM equals 48 divided by 2 is 24. Is there another way I could have done this? Starting here, is there another way I could have done it? Anybody remember from last year multiplying by the reciprocal to get rid of those fractions? To multiply by the reciprocal, that's one way you could do it. You could also plug 2 into your calculator, 2 divided by 3, and instead of 2/3, write that as a fraction, 0.6667, and use the fraction. You would probably get a decimal here, probably come out to 0.24 point something, so you'd be close. So that's another way you could go about it. But because P is a centroid, SP is 2/3 of the way across to the middle of the other side. Questions there? All right. So before we talk about our next theorem, we need to talk about our next kind of segment. An altitude. And in parentheses, I'm going to put height, because in the past we've used these two words kind of to mean the same thing. So altitude and height. So altitude is a perpendicular segment from a vertex to the opposite side. So we're going from a vertex to a side again. This time we're going the perpendicular segment, and I need to put an or in here. Or to a line containing the side. And when I draw a couple of pictures, this will make more sense. So if I have a nice acute triangle, I just go from the vertex at a 90-degree angle to the opposite side. It's not necessarily the bisector of the angle, it's not necessarily the bisector of the other side, it's just from the vertex perpendicular to the other side. So that would be an altitude. If we have a right triangle, the perpendicular segment from this vertex to this side is that side of the triangle. So that is an altitude. So the altitude could be a side of the triangle. And if we have an obtuse triangle, here's why we had to write that or, is to find the altitude here I have to extend this side out to go 90 degrees there. So this is an altitude. So that's why we had to put that or, because with an obtuse triangle I have to extend the side to find the altitude. Yes?
Like altitude, how is extended to median?
So the altitude doesn't have to go to the middle. That's how you tell the distance. The median goes to the middle of this side. The altitude just has to go at a 90-degree angle.
Okay.
So they do end up in the drawings. They look kind of the same. So that's what makes them tricky to keep them separate. This also looks like it could be the perpendicular bisector, but it's not necessarily cutting that side in half. It's just going at a 90-degree angle. Okay. Sometimes you just have to know what is an altitude, what's a perpendicular bisector, what's a median. They have to know which one is which. So our theorem. Before we do our theorem, let's do an example of deciding which is which. So let me draw a triangle. And for this one we want to know, are we talking about an altitude, a median, or neither? And I'm going to call this A, B, C, D, and E. How about AC? Segment AC. Segment AC, an altitude, a median, or neither? Median. AC is a median because it goes from the middle of one side to the opposite vertex. So that is a median. How about segment AB? Altitude, median, or neither? Neither? What is segment AB? It's just the side of the triangle. So that's neither. That's just the side of the triangle. How about AE? That is an altitude. It goes from the vertex to a line 90 degrees to a line containing the opposite side. So the median has to go to the middle. The altitude just has to make a 90-degree angle from one vertex. All right, so let's talk about our theorem. So based on what we've talked about on Friday and what we talked about with the centroid, what are you going to guess is going to happen when we draw three altitudes of a triangle? What have we been talking about with our three segments? What have our three segments been doing? They cross, they're concurrent, they intersect at the same point. And that happens with the altitudes also. So our theorem. The three altitudes are concurrent at a point, concurrent, they all intersect at the same place, point called the orthocenter. Now the orthocenter is not a circle that connects all the parts of a triangle. We can't draw a circle, anything like that. So, and we really don't talk about the circle that we get from the orthocenter. Well, all we need to know about the orthocenter is it's where the three altitudes intersect. And what I would say, what I told the last class, if you understand from Friday, if you understand what the incenter and what the circumcenter is telling you about the triangle, about the distances, I'm more interested in that than the constructions themselves. So what I really want you to do is understand that how the points are related to the triangle. If the construction is confusing, I'm not as worried about that as you understanding how these segments are related to the triangle itself. So the three altitudes of a triangle concurrent at a point called the orthocenter. And the orthocenter, it's not the same distance from anything special, but it's like the circumcenter. It can be inside, on, or outside the triangle. So if we have a nice acute triangle, our orthocenter is inside our triangle. So it's inside an acute triangle. If we have a right triangle, we already drew a picture here. The altitudes of these two sides are the sides of the triangle. So this is a 90-degree angle, and this is a 90-degree angle. So there's our orthocenter. So it's on a right triangle, because these two are the altitudes of these two sides are altitudes. And it's the obtuse triangle, just like the circumcenter, where we get our orthocenter outside. I'm trying to draw one so the orthocenter doesn't get too far outside. All right, let me extend these sides. We have to extend these to get our altitudes. there's the altitude to one side. There's the altitude through the vertex to the other side, and then to our third side would be right here. And then these would be our 90-degree angles. Make this a little shorter. So there would be our orthocenter. So the orthocenter is outside an obtuse triangle. So just like the circumcenter or orthocenter can be inside, on, or outside the triangle, where the three altitudes intersect. So questions about the orthocenter? All right, I want to do one example. There are a couple of these in your homework where we need to find or use coordinates to find the orthocenter. So I want to do an example of that. So I'm going to write up our steps here, and we'll do an example following these steps. So this example brings together a lot of stuff that we've learned over the course of the year. So step one, I'm going to say sketch the triangle. So we have the coordinates. We're going to use the coordinates to sketch a triangle. We need to find the slope of two sides. Our orthocenter comes from the altitudes, so we need a perpendicular line to the two sides. So we need to write the equations of perpendicular lines to the sides. Through the opposite vertex. Now before we go on, let's remember how are slopes of perpendicular lines related. Slopes of parallel lines would be congruent. Slopes of perpendicular lines, opposite reciprocals. So our slopes are opposite reciprocals. So we're writing the perpendicular line, so we find the slope of the sides, then we do the opposite reciprocal, the negative reciprocal. And then we're going to, and because we go through the vertex, we're going to use point slope form. I'm going to put that in parentheses, point slope. And we're going to use substitution to find where the lines intersect. And the point where they intersect is going to be our orthocenter. All right, so let's look at an example. So we want to find the orthocenter of the triangle with vertices at 3, -2, 9, -2, and 5, 6. So first thing I'm going to do is sketch a little picture of the triangle. It doesn't have to be a perfect sketch. You could use graph paper if you wanted. I'm just going to kind of guesstimate to get an idea of what it looks like. So I'm going to go over 3, down 2. I'll call that point 3, negative 2. Now I'm going to go over 9 and down 2. And then we're going to go over 5 and up 6. So I'll say this is 5. So my triangle looks something like this. Not perfect, doesn't have to be perfect. Just want an idea of what it looks like. Now what I'm going to do is find the slopes of two sides. I'm going to pick one of the easiest ones. So I'm going to find the equation of that altitude, and I'm going to find the equation of that altitude. And my picture is just a sketch. It's not, I can't use my picture to figure out where these intersect. I need to do a little more work on it. All right, what kind of line goes between 3, negative 2, and 9, negative 2? What would we call that line? It doesn't change in the x direction. Doesn't go up. So what's the slope of that line? I'm going to say slope between what's the slope of the line if it doesn't go up at all? So our slope is rise over run. What's the rise of this line? 0. There's no rise. The slope is 0. That's a horizontal line. The perpendicular line is going to be vertical. And we want it to go through 0.56. So what's the equation of a vertical line that goes through the 0.56? On this line, does x ever change? If I'm going straight up, x never changes. So the vertical line is x equals 5. That's the equation of a vertical line. X equals something. So the equation of this line is x equals 5. So we have the equation of one of our lines. Now we need to find the slope between these points. Between 5, 6 and 9, negative 2. So how do we find the slope between 2 points? Let me give you a hint. x1, y1, x2, y2. Remember how to find the slope? y2 minus y1 over x2 minus x1. So I get negative 2 minus 6 over 9 minus 5. So I get minus 8 over 4 or minus 2. So the slope of this line is negative 2. What's going to be the slope of the perpendicular line? We said it was a negative reciprocal. So what's the negative reciprocal of negative 2? And flip it over. 1 over 2, 1/2. The slope is the negative reciprocal, so 1/2. And it goes through the point 3, negative 2. So now I can use my point slope form. y minus y1 equals a slope 1/2 x minus x1. Point slope form. So I get y plus 2 equals 1/2 x minus 3. Well, the other line is x equals 5. So I'm going to substitute that in, x equals 5. So y plus 2 equals 1/2 5 minus 3. Y plus 2 equals 1/2 of 2. Y plus 2 equals 1. Subtract 1. And y equals 1. So our orthocenter is at the point 5, 1. That's where those two lines intersect. So you can see my drawing not very good here. So we found the equation of both of those lines using the slope. Use point slope formula. Let me remind us what that is. Y minus y1 equals m times x minus x1. And this point is x1, y1. I wrote that on the wrong line. So I know that y equals 1 and x equals 5. So that's my point. Y equals 1, x equals 5. So that's my orthocenter. At x equals 5 and y equals 1. So, that was because this is a horizontal line. So we wanted the vertical line that went through this point. So we said that y never changes. So x equals 5 is the equation of that line. All right, so there are a couple of these on your homework. This kind of problem, there's a lot going on. It's not a major type of problem that we're going to ask you to do. There are a couple on the homework, but it involves things, all the different kinds of things that we've already learned. So that's why I wanted to go through that. All right, let me give you your homework, then I'll pass back your folders. I don't think we have time to go over the homework, so I just want to pass back the homework and collect it. All right, there you go.